So this is Kota Uenishi. I'm giving a talk about our use case of Apache Ozone behind our simulation and AI workloads. Why use Apache Ozone for our AI systems? One reason is because it has an S3 compatible API, and so it's very easy to obtain data or put data by any clients. So also the small files problem we had in HDFS is well addressed. So why S3 API is important is because our workload is a deep learning, and its software stack is most doesn't fit well with JVM clients and systems that consists of Python or C++, and it also runs MPI, and the GPU libraries and systems are mostly complicated, very complicated, and needs native code execution. So also one big thing about Apache Ozone is its power community from Hadoop, and please see also my blog article about the Apache Ozone that we ran for more than a year. So let me describe our workload from the storage-centric perspective. The workload may have a lot of different view from my colleagues, but this is my view. So we have huge compute cluster consists of GPU, more than 1,000 GPUs, and also a set of our in-house developed AI training accelerators. So on the other hand, we also have an Ozone cluster and a few another HDFS cluster, but we are mainly using the Ozone. So so the typical machine learning is train a model from real data and export the smarter trained models by training the model with data by using GPUs for optimizing models. But our use case is we also use simulations. Simulation is could be is a scientific simulation that is based on the first order simulations or scene generation rendered from the 3D models, which will be described later. But here is that we generate huge amount of data from our compute resources and store, kind of save into the storage cluster. And on training, we read those generated images for optimize the model, like to let them recognize those images, and the amount of data is much more than real data, so the model it can easily get much smarter than just by training by real data. So let me describe right use cases, the left side in this chart. So yeah, in essence, the data generation is write workload to our storage cluster. So let me describe them. So the write workload is just saving the result of simulation, which we can say the one example of our simulation is like this. So we scan these real objects for using several cameras, and we construct those images as 3D models, and we can we can render this kind of arbitrary scenes, or even make it high resolution. And further, moreover, we can generate arbitrary images constructed by multiple or arbitrary number of objects. And what is great about this simulation is, like, we don't have to annotate anything, but we already know what object is it, or like this segmentation is, it's really easy to generate the ground truth, and it's really easy to train those models with huge number of images, especially when we have enough real quality of rendered images. So the left side is not a real photo, but rendered image of these 3D models. So we can, train a model like really close to real, but it's fake image. So the workflow is very simple and straightforward. Just model the real, scan the real objects and reconstruct as a 3D model, and render the scene images, and render the scene images by using GPUs as single scene images, and by using, and also generate the answer or annotation data from when we generate, and we trained deep learning model from those images and also annotated data we already have, and just check the quality. That's really straightforward, except the fact we are using not generated data, but not the real data. So this is that was our use case. But if we generate so many images, then we could have such problem like this. So if we store a single image file per scene, then the number of images gets huge. Like we have several aspects of problems. In the speed aspect, the auto manager gets a bottleneck in our observation, we think, and especially when we put the data or we list those files. Also, the quantity, from the quantity perspective, not just the amount of images are huge. Like it's close to a billion, and not only the images, but we already have more than a billion files in our single Ozone cluster. So, but more than 99% of those files are used for this workload. The portability problem is that we have, it's not easy to check all those images are valid. Like if checking the checksum of a billion files, we have to calculate billion checksum, and that's not easy work. The pros for the single file per scene is that the performance. So data node has several optimization tricks, so we can put and guess very fast for smaller files. So the first small files problem we made in our real cluster, but on the billion keys, is when we try to list the keys recursively. The listing keys overwhelmed the CPU cores of auto managers for decoding the binary from the RocksDB using proto buffers as a Java object, and printing them as HTTP, XM, and XML. So the flame graph, this flame graph denotes that is taken from the Ozone manager using the async profiler, but the 78% of this is used for the ListKeys, and this is only for the RocksDB put and get. So these more than half of CPUs are used for decoding the protocol buffers. So how we address this problem is we just rate limit. So the Guava is already included into Ozone. So I just added a few lines to actually block the request before entering into the process of listing keys in Ozone managers, and rate limit is currently on 256, and that was just enough for making CPU room for getting keys or putting keys for other applications, and Ozone manager gets working very well. Also, the ListKeys get very slow is not true, because I think why the Ozone manager was overwhelmed by the ListKeys was by some applications that doesn't behave very well, and I think the ListKeys is not necessary for such applications. So the problem in putting keys here is also described. Our observed peak on putting keys to the Ozone cluster is about 1,000 puts per second, and that made the Ozone manager mostly saturated in our observations. And the possible causes could be a giant rat lock on buckets in Ozone manager, or could be saturated data put in the data nodes because they use hard disk drives. Also, the communication between the S3 gateway and Ozone manager or other components is per connection based, as some of you may know, and that is managed as a HTTPS 440. And I heard that will be addressed in Ozone 1.3, I guess. And our workaround for such huge amount of putting keys is to just reuse files in the application. Is done by our internal users, like keep a wider image and not cutting those images down to pieces. Also, more general workaround is to make an archive for such like 10,000 or 100,000 files as a single zip images, and reduce metadata overhead in the Ozone manager. And then we'll be able to virtually put more images per second than we had. So the cost of having an archive for that is that we can't get the benefit of small files optimization elsewhere we have in Ozone. And also I will address later that the slow, when we have a zip archive, then directly reading images from the zip file makes it is a bit slower than we have in a flat format. So what's wrong with archived zip files here is the good point of before cons. I have to mention about pros is that it's really easy to maintain the dataset. The validity of dataset is very important. So like maintaining a checksum for zip file is really easy than maintaining checksums for each images inside the archive. So also zip is de facto standard, so it is supported by Python and inside the standard library, so you don't have to install any additional archive formats or libraries. And the cons for that is that the read latency is 4 times worse than the flat files format, and that is not good for deep learning training, and we can have small file optimization in data nodes. So let me describe the latency here. So, but you might think a workaround or addressing these issues will be like prefetching files or pipelining the read to the zip. But let me describe from the basic about these reads of training AI models with generated data. So regardless of whether the data is generated or your data, the workload or I/O pattern of deep learning does not differ so much. It's just essentially a repeated random read. So the example code here is enough to describe the workload. So the session is repeated. Session of reading the whole data is repeated several times. Like a training image is typically a 19 times repeated read of all data, and the images are shuffled every time. So you just can't assume bulk read or sequential read in this case. Also, the images are both being read each time, because all of those images cannot be cached inside the memory, because the application uses a huge amount of memory. And this is essentially deep learning training, and I won't describe. But sorry, it's very simple. But so the data set is shuffled and split into pieces and feed it to multiple GPUs to parallelize the training, and they are fed in the GPUs. And after the optimization in GPU is done, then it comes back to the first shuffle again and again and again. They are repeated like 90 times. So typical numbers in such training is like currently the required speed of feeding GPUs is mostly about 1,000 images per second per GPU. So and typical GPU computer includes 8 GPUs per server. So typical data delivery requires 8,000 images per second for node. But in our observation, the whole Ozone cluster can read 7,000 images, I would say that files per second for Ozone cluster, and that is random read for flat files. And on the other hand, the total observed sum of the disk I/O disk read is that around 9 gigabytes per second. So the disk I/O and network bandwidth is enough, I guess. So in a naive manner, we can only feed 7 GPUs, even though we have more than 1,000 GPUs. The workaround here would be caching those data in node local storage, or caching those data in shared cache server like Nginx or else or whatever in a remote and concentrated centralized server. So here's benchmark of repeated random read. So I ran a repeated random read for 1.28 million dataset of files, we can say files twice for archive zip file. This is a single zip file that includes 1.28 million images in a single zip file stored on a local file system, or the flat image 1.28 million files on Ozone, or the same archived zip file on Ozone. So after the first epoch, we read the 1.2 million files, then all of them are cached in a local storages. So after that, the level of latency are mostly same in the later half of these images. So in the first half of this benchmark, the latency fluctuation is much larger in zip than flat. So the green lines are on zip files in Ozone, and the orange line is flat image files in Ozone. So the latency is apparently better for flat files, but we know that we have other small files problems, so we can naively accept this result. And zip file is much easier to manipulate or handle or maintain, but the latency is not that good. Like we have 400 milliseconds to get a single image from such a zip file. On the other hand, reading from the local NVMe is very fast, like less than 100 milliseconds or like 10 milliseconds latency for randomly reading a single image file. So this is our solid cross suspect that runs the benchmark in previous slide. So we have 12 data nodes, and each data node has 36 14 terabyte hard drives. So I think we have more than 300 hard disk drives, and each node has a 512 gigabytes RAM, and the CPU is not that fast. So it's a Xeon Silver CPU, and the network is fast. So we have 200 gigabyte Ethernet network card, and all of our network is built on top of 100 gigabyte infrastructure. And also the benchmark client has 4 NVMe drives, so that is very fast, and the same Intel CPU as the Ozone clusters. So the resolution for resolution for reading image files from a large zip that includes millions of small files is having a Sparse file cache like this. So the 16 megabytes buffer for prefetching the data in the large zip is thrown out if we don't cache in a locally, and this cache is very important, and even if we run it as random read. So on a single session of reading a single image, then the system reads 60 megabytes of prefetch buffer, but only uses the first 100 kilobytes for images that is included in zip file, and that is read as a dataset. But the other more than 15 megabytes buffer is thrown out if we don't save them, cache them. And if we keep them in a local storage systems, then it can be read directly from this local file without fetching from remote Ozone. Then this will work as this prefetched part will work as a kind of random read cache, and when we repeat this kind of prefetching, then the Sparse file cache will be filled with the actual data fetched from the Ozone, and then when we can say the cache is warmed up very well. Also, the latency penalty is very large if we read in like 16 megabytes, but the latency penalty does not differ so much even if we read 16 megabytes or single megabytes or just read the amount of image like 100 kilobytes. So if the latency is the same, then it's much better to fetch as much data as we can. Then we can fetch and cache more images than just reading this required images. So this is basic idea of sparse file cache I implemented into our library. So I took the benchmark about that sparse file cache idea, and it is rendered as a red line here, but we can see the difference very well. So let me change the scale of the graph. So the red line is the new sparse file cache here, and it need 5%, like reading the first 5% of the whole zip file on fetching those data, and I think we can safely that the cache is warmed up very well by just reading the first 5% of images with prefetch, and it is even much faster. It's even faster than reading from NVMe zip. This is possibly because the buffer size is different, because I used 16 megabytes, but local file system adopts the 4 kilobytes page size. Then the cache will be warmed up only with the 4 kilobyte unit. So, and after reading the first set after the cache warmed up, the level of latency for the sparse file cache is almost the same as NVMe local file cache. So the summary here is that we generate from our huge compute infrastructure and maintain the generated billion of images files for AI training, and in that case, small files problem, which is said to be solved in Ozone, was addressed, but it kind of resurrected in much harder scale, like billions of image files, and in a different form, like a slow listing keys, and which is workarounded by rate limiting, and possibly will be addressed by file system optimization, which we don't enable, but also the slow put was worked around by archiving the 10,000 file as one zip, and it had a side effect of having a slow random read for an archive file, but it will be worked around by the sparse file cache. So, thank you.